everyone. I'm Lisa Abbo, the veterinarian here at the Marine Biological Laboratory, and today I'm going to talk to you about water quality. So we care for a lot of aquatic animals here at the Marine Biological Lab, and in addition to providing for their basic needs, high quality food, shelter, safety from predation, we also have to make sure that they have good clean water in which to live. One of the ways that we do that is that we monitor the parameters of the water on a daily and in some cases weekly basis. So today I'm going to go through the process for doing that and explain a little bit about why each parameter is important to monitor. So one of the things that we know about animals in general and also in aquatic animals is that stress can lead to a spike in cortisol within the body or some sort of stress hormones. It's not always cortisol for every animal, but stress hormones, which can then result in immune compromise. And one of the things that can be very stressful for animals is poor water quality. So try to imagine yourself in a small environment where there's no access to any fresh incoming air, for example. Everything that you do in that environment stays within that environment. And imagine yourself in that small enclosed space after about a week. You would probably start to have some ill effects. You'd probably start to have some respiratory problems. You'd probably start to have some GI problems. A lot of things can go bad when you are in a confined space. So the same thing is true for aquatic animals. So when they're living out in the ocean, excuse me for 1 second. One of my tests is just finished. I'll explain that in just a minute. But when you're living out in the ocean, you essentially have an unlimited supply of fresh water, or clean water, I should say. It might be a marine environment where it's salt water, or it might be a freshwater pond. But the point is that you have access to unlimited amounts of water. And so all of the waste, all of the metabolic waste that you produce gets flushed out. And you always have access to good, clean water. But the minute you put an aquatic animal into a tank, you sort of lose that ability. And so you're essentially creating an environment where waste products are going to build up, and that's going to make the animals stressed, and it's going to make the animals sick. Okay, so I'm going to talk a little bit about the nitrogen cycle. So this is a really important concept when you're dealing with aquatic animals. So it's basically the process of converting the toxic form of protein metabolism, which for fish is ammonia, and converting it to a much less toxic form. And so in the microenvironment, you have bacteria that feed off of the ammonia, and they, in the process of that, convert it to nitrite. And then there are other bacteria that then take that nitrite and convert it even further to nitrate. And nitrate is much less toxic to fish than both ammonia and nitrite. And so that's the simplified version of the nitrogen cycle. And I'll show you a little schematic in a few minutes, and you can take a look at it a little bit more closely. And you can also look it up and read about it. It's something that occurs in the soil as well, not just in the water environment. But it's a really important concept for us to keep in mind. And so when I'm doing water quality, one of the things that I'm measuring is ammonia. And I'll show you my first test that I just finished doing, and I'll show you what that looks like in just a second. Okay, so what I've done here is I've used some reagents to run a test of ammonia concentration. And this is a screening test that I first use. I take all of my water samples and I put them in these wells here, and then I mix them with the reagents, and then I look for a color change. So if there are high concentrations of ammonia, it would turn a dark green color. And if I see that, then I can run a finer test and actually get a value for the ammonia. And that's where I run that on the actual spectrophotometer there. Right now, the test that I've run, the timer has just gone off. And you can see that they're all still kind of a yellowish color. So no high levels of ammonia, so that's great. So this is the very simplified version of the nitrogen cycle and what's happening. So as I mentioned before, fish, through the process of protein metabolism, are breaking those molecules down, and they're being excreted in the form of ammonia. and that is primarily excreted through the gills, but also some is excreted through the urine as well. And then through the process of nitrification, that ammonia is converted to nitrite, NO2 down there in the bottom right, and then that is further broken down to nitrate, NO3. And nitrate is the least toxic form for fish, and so they can tolerate quite high concentrations of nitrate, but they really can't tolerate much ammonia or nitrite at all. And depending on the aquatic species, cephalopods, for example, are very sensitive to those nitrogenous compounds, and so their tolerance is even lower than fish. Similarly for corals also can't tolerate those metabolites building up in the water either. So what are the ways that we can sort of flush out these nitrogenous wastes in a system where, say, we have a large tank and we don't have good biological filtration, which are those beneficial bacteria? Then what are some of the ways that we can kind of keep that water flowing, keep the water flushed out? Well, one of the things that we do here at the Marine Biological Lab, and a lot of facilities maintaining large volumes of aquatic animals will do, is they'll have an open seawater system. And so because we live here right on Eel Pond, on Great Harbor there, we have the benefit of having access to unlimited amounts of clean seawater. And so what we do is we pump in that seawater from the Great Harbor across the street, goes through a series of pipes, goes up to the top floor of one of the buildings across the way, and then is gravity fed down into the tank room in this building here. And what we essentially can do is provide these large tanks with essentially just unlimited amounts of clean seawater. And so this is considered a flow-through system. So the water is flushed out continually throughout the day. And the fish, it's almost as if they're living out in the wild where they have access to fresh, clean water all day throughout the day. And so we don't have to worry too much about buildup of these nitrogenous wastes. We still measure it once a week just to make sure, and we have other systems that are called closed systems where we do have to worry about it. So we run all these tests together, and that way we can make some comparisons. So the other kind of the opposite extreme of that would be what I just mentioned, a closed system. So that's where you essentially have a static tank full of a given amount of water, and that doesn't change other than just you doing manual water changes each day. So that's a completely closed system. And in those systems, we worry very much about the buildup of waste products. And we have to be, in some species in the cephalopods, for example, they need to have their water changed every single day. Otherwise, that buildup in ammonia overnight can actually kill them. So we have to be very, very careful about that. And then somewhere in the middle is a semi-open or semi-closed system where you have a static tank, but then you have a certain amount of fresh water coming in continuously, so a slow drip or maybe a slow trickle. And so that water is slowly but still continuously being turned over throughout the day. So the other parameters that we measure on a daily basis are pH, salinity, dissolved oxygen, and temperature. And the reason these are important is because they can fluctuate based on the number of animals in a system, based on the time of day. And so it's really important to keep on top of these. We know that small changes can sometimes have very dramatic effects on the health and well-being of the animal. So that's the other reason that we need to keep real close tabs on those. So dissolved oxygen, just as it sounds, is just the amount of oxygen that's dissolved in the water. And that oxygen gets used up by not only the animals living in the water, but also bacteria that are living in the water. So if you have high animal load, high bacterial load, then that oxygen can get used up really quickly and be depleted, and so it's not available for the animals to use. The other thing that we keep a real close eye on is the pH. So the pH, animals have evolved to operate within a very narrow range of pH. So most animals are quite sensitive to changes in pH. And so you can see overnight, for example, the pH will drop. So the first thing in the morning you'll come in and the pH will be low, but then it'll gradually rise throughout the day. And the reason is because of cellular respiration that has been occurring overnight. And so as animals are metabolizing the food that they've ingested, they produce CO2 as one of the byproducts. And so overnight, when the animal is just resting and metabolizing, that CO2 builds up. And then in the morning, because of that high CO2, we'll see a drop in pH. So there's a really nice, simple equation that I'll show you in just a minute that explains that drive. And it also explains a little bit about climate change and why elevated CO2 in the atmosphere results in ocean acidification. So this is a super simplified equation that I was talking to you about just a minute ago about pH. And so you can see if you look to the right of the equation, as CO2 builds up, it pushes the equation to the left. And what you end up with are higher concentrations of hydrogen atoms, and that's what creates the low pH or acidic water. And I mentioned this already, but bodily systems have evolved to function at a very stable pH. And most animals do not tolerate any kind of change in pH, especially if that change is very abrupt. So this is a really important water parameter that we need to keep very close tabs on. So I'll mention a few of the different methods that you can use to measure the parameters that I've been talking about. So one of the, probably the most simplest method is this drop kit. So you can get these just at a regular pet supply store. This is what a lot of people with home aquariums will use. You simply mix the reagents according to the directions, and then you hold it up, and after the time has gone by, and you compare it to the colors here. And then you use your eyes to just most closely match the color, and then it'll give you the reading. It'll tell you what the value is. The problem with these kits, though, are that they're pretty wide ranging. And so, for example, for ammonia here, it goes from 0 to 0.25 milligrams per liter. And we know that ideally for fish, they should be at 0. But fish can tolerate, some fish can tolerate up to 0.01 milligrams per liter. Cephalopods, because we have a cephalopod culture here, so I'm always referring to cephalopods, they really should be at 0. But so up to 0.25, that would probably kill a cephalopod. And so this isn't a fine enough scale to use here in the lab. So what we use is this machine called a photospectrometer. And what that does is it measures the wavelength of the light passing through, and then it gives us an actual value, a numeric value, telling us what the concentration of whatever product it is that we're looking at. So this is a much more precise method, and this is what we use on a weekly basis. For pH, salinity, and dissolved oxygen, we have these little handy probes here that we can use. So just a standard pH meter that you would find in any lab. This one just is a handheld that we can carry and measure elsewhere, tank side, which can be really convenient. The dissolved oxygen I already mentioned before. We have a temperature probe in here. And then it also has a salinity probe. But I tend to like to use this refractometer. It's very low tech. It gives us accurate results. We just put a drop of seawater there, and then we look at it, and there's a scale in the eyepiece, and it tells you exactly what the salt concentration of the seawater. So as far as what normal values are, it really depends if it's seawater, if it's freshwater, where in the world you are. Different oceans have different normal levels. But generally speaking, seawater should be around 35 parts per thousand. Here it tends to run a little low, probably around 33 is pretty normal for us here in Woods Hole. pH of seawater usually should be somewhere around 8.0 to 8.2, kind of depends on where you are. Here we tend to get the high 7, so 7.9 up to 8.1. It kind of varies. Depends a lot on rainfall. If we've had a lot of rainfall, then the pH will drop a little bit. Dissolved oxygen ideally should be 100%. And if it's not, it's one of the things that can clue us in that there might be something going on. And so we measure that on a routine basis as well. And finally, there are other things that we can measure. Alkalinity, for example, phosphates, for example. Depending on the needs of the researcher, we will measure those, particularly for people keeping coral. They need to know those values because we know that those animals are very sensitive to any kind of changes. And so really just sort of depends on what the researcher is after, what the study is that they're doing, and that pretty much sums up what we do here in terms of water quality. Again, we just really want to focus on ways that we can make sure that the animals are as healthy as they can be. That's good not only for the welfare of the animal, of course, because we're equally concerned about that, but it's also good for the research. So we know that the fewer variables there are, the higher quality the research will be, the more reliable it is, and the more reproducible it is. And so we make every effort possible to try to maintain those very strict parameters within a very narrow range. So that sums it up for me. Next time I'll talk a little bit more about animal health, the things that we look for, how we know when a fish is healthy, what types of health problems we might see in a lab setting, and how we manage them. So thanks for joining in.